And here's another one. This is the second one that I'm doing for the force unit. And what we're going to talk about today for this video, very briefly, is going to be gravity. Remember, at the end of this one, I'm going to want you to watch this video, summarize it in one sentence or two maybe, and then any question that you might have about what we're talking about. Okay, so let's start with this. I want to talk about gravity, or the force of gravity, which we also call weight. So let's see some examples of gravity, like a little girl jumping off a diving board.
Here you go, Zana. Off the big 3-meter board.
Or we could have Felix Baumgartner jumping out of a balloon from over 20 miles high. I don't know if you were able to read that, but right there on the video it says free fall. And then, well, what about some other ones? Well, here's a video that took place on the moon. And so you had the astronauts that were on the moon had a feather and a hammer, and they were dropping them together. Now, what's there on the moon, there's plenty of gravity, but there's no air. Let me skip forward a little bit.
My left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of the gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So, and then lastly, we have the gravity in Angry Birds. So, what do we see about these things? Well, one of the things I tried to point out to you is that if we ever drop something on Earth, it will always accelerate at the same rate. We call that acceleration g. The g has a value of 9.8. I was about to say 10, but I'll get to that in a second. It has acceleration of 9.8. Okay, how did I do that? There we go. 9.8 meters per second per second. I ask you to use 10 in most of your calculations, and the reason why. 10 is just easier to work with, and we don't really introduce any large size error there. Well, that's okay. So what does that do for us? Well, it allows us to figure out the force of gravity. It's going to equal to the mass of whatever it is times g. Let's think about Felix Baumgartner again. He's up in the gondola of his balloon. He jumps out. And the only thing acting on Felix right now is the force of gravity. Okay? There's no air where he was. Or we can take that little girl on the diving board. Now, the amount that the air would be slowing her down would be very, very tiny. We can effectively say that the air had no effect on her. The only force is that. Even on the moon, let's talk about the hammer. It's a really bad picture of a hammer. That's falling with a force of gravity. The force of gravity, I should say, is pulling it down in all those cases. So, force of gravity is mass times gravitational constant. In the case of Felix Baumgartner, I'm not sure how much he weighs. Let's say that he has a mass of about 85 kilograms times 10 meters per second, and this gives us 850 newtons worth of force that he's being pulled down with towards the earth. Okay, this is his weight, and this would work for Felix Baumgartner, and it would work for the little girl on the diving board. Where it doesn't work is here on the moon. Or you'd think. Because if we go back to that video, we go back to this video, go back to the moon video, this one over here, right back here, it might be obvious that these things are going pretty slow.
Well, Falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
It took about 1.5 seconds for those things to fall, and it would take less than 1 second for me to drop a hammer like that and have it hit the floor. So, why the difference? Well, I can't really explain all the reasons why just yet. Right now, you're just going to have to take it. I'm just going to have to be able to tell you that, yeah, it happens. And it does have to do with how much mass that the moon has. So, the moon has 1/6 of the mass that the Earth has, or approximately 1/6. So actually, the acceleration due to gravity on the moon is 1/6 the acceleration due to gravity on Earth. So, if we had Felix Baumgartner at 85 kilograms, and he was on the moon, that would be multiplied times 10, but divided by 6. So 850 divided by 6, 850 divided by 6, well, that goes in there once, 6, 2, 5, that goes in 4 times, 4, 10, and that goes into that once. 6, 4, 141.8 newtons. 141.8 newtons. Now, you will see problems like this on the test. We'll have problems along the lines of, if the force of gravity on this planet is this, what do they weigh? If they accelerate at this, what is the acceleration due to gravity? So you may see those kind of problems. It's going to be very straightforward. Their weight, or the force due to gravity, is going to equal mass times whatever the gravitational constant is on that planet. Okay, we'll have some chances to practice this. So thank you for paying attention. Remember, write down a summary of this, and then write down one question you want answered. So, thanks a lot. Take care, and may all your problems have solutions.